I want you to think about something that's probably within arm's reach right now. Not something dramatic, not something that looks impressive, something so ordinary that you might genuinely struggle to remember the last time you noticed it. And that is glue. Somewhere near you, in a drawer, in a bag, on a shelf, there's probably some version of it. A glue stick from a school bag, a roll of tape in a kitchen drawer, a tube of super glue that has very likely stuck itself partially shut. And in the room you're sitting in, whether you can see it or not, there are dozens of objects that are held together by adhesives. The screen you might be watching this on, the soles of your shoes, the spine of any book you can see, the furniture around you. Glue is everywhere. It is, in the most literal sense, holding the world together. And it is the most overlooked technology in human history. We tell the story of civilization through the loud inventions. The wheel, fire, the printing press, steam engines, computers, the things that made dramatic noise, that caused visible change, that could be pointed to and said, there, that is the moment everything shifted. Glue made no noise. It held things quietly. It enabled every other invention by making composite structures possible, by allowing different materials to work together, by joining the small to the large, the soft to the hard, the lightweight to the strong. And here is the fact that I think should reframe the entire story of human intelligence. The first creature to make glue was not Homo sapiens. It was a Neanderthal. 200,000 years ago, before our species had fully developed, before we'd arrived in Europe, before any of the things we credit our species with inventing, a Neanderthal somewhere in what is now Italy figured out how to heat birch bark to a precise temperature to extract a sticky black tar and use that tar to fix a stone blade to a wooden handle. That is the oldest known synthetic material in human history, older than pottery, older than woven textile, older than almost everything we consider the hallmarks of human ingenuity. And it was glue. Hi, I'm Alexandra. Welcome to the Hidden Life of Things, everyday history for anyone who's ever looked at something super ordinary and wondered, how did this actually get here? Let me spend some time on that Neanderthal because I think they deserve it. Neanderthals are not the brutish, club-swinging cavemen of popular imagination. That image has been thoroughly dismantled by modern archaeology and genetics. We now know that Neanderthals buried their dead, possibly with flowers. They used pigments, possibly for decoration. They made jewelry from eagle talons and shells. They interbred with Homo sapiens. If you have any Europeans or Asian ancestry, roughly 1 to 4% of your DNA is Neanderthal. They were not a different and lesser kind of creature. They were a related kind of creature with complex cognitive lives, social structures, and cultural practices. And 200,000 years ago, they were making glue. The evidence comes from archaeological sites in Italy and Germany. Small lumps of dark, sticky tar found on Neanderthal tools. Tar-covered stone flakes, clearly hafted, meaning attached to handles. The tar itself has been chemically analyzed and identified as birch bark tar, a substance produced by heating birch bark to a specific temperature range in the absence of oxygen. Too hot and the bark burns, too cool and no tar is produced. The target temperature is quite narrow, roughly 340 to 370 degrees Celsius. Researchers at Leiden University spent years trying to work out how Neanderthals could have achieved this without ceramics, without kilns, without any of the control mechanisms we'd expect to need. They eventually found that a surprising simple method worked. Roll birch bark tightly, place it in a hot embers with a stone on top to limit oxygen, and enough tar condenses on the surface to haft a small tool. The simplest method, requiring only fire and birch bark, could work, and more complex methods produced larger quantities. What this means is extraordinary. To produce birch bark tar, you need to understand materials, to know that this specific tree produces this specific substance under these specific conditions. You need to plan ahead, gathering the birch bark before you need the tar. You need to control a process, managing heat and oxygen in a way that produces the desired outcome, rather than just burning the bark. And you need to have invented the concept of hafting in the first place, the idea that attaching a handle to a stone tool would make it significantly more effective. Archaeologists use the word hafting, attaching a blade to a handle, as a marker of cognitive sophistication. A stone blade on its own is useful, but limited. You have to hold it close to your target. You risk cutting your own hand. Your force is limited to what your grip can manage. A hafted tool, a stone blade glued to a wooden shaft, completely transforms what's possible. You can throw it, you can use the mechanical advantage of the handle, you can hunt from a safer distance, you can apply more controlled, directed force. The leap from bare stone to hafted tool is one of the most significant technological transitions in human prehistory. And the material that made it possible, the substance that joined the stone to the wood, was a synthetic material deliberately manufactured by a being that was not even our species. Glue is not a footnote in the story of human intelligence. It is evidence that intelligence itself, the capacity to understand materials, plan processes, and engineer composite solutions, predates our species entirely. Fast forward from the Italian hillsides of 200,000 years ago to the Valley of the Kings around 1323 BCE. Tutankhamun, the boy pharaoh who died aged about 19 in circumstances still debated by historians, was buried with extraordinary care. His tomb, discovered by Howard Carter in 1922, contained over 5,000 objects: furniture, clothing, jewelry, chariots, statues, the accumulated material wealth of a royal household intended to accompany the king into eternity. And when conservators at the Cairo Museum analyzed that furniture carefully, the inlaid wooden chests, the chairs with their decorative panels, the shrines with their gilded surfaces, they found animal glue, specifically a collagen-based adhesive prepared from animal hides and bones used to bond the veneer surfaces to the wooden cores of the furniture to secure inlays, to reinforce joints. 3,000 years old, and the glue was still working, the veneers were still bonded, the inlays were still in place, the joints were still sound. This is worth pausing on. The furniture made for Tutankhamun's tomb is extraordinarily fine. Thin sheets of rare wood or ivory or glass paste laid over wooden cores, creating surfaces of visual complexity and beauty that could not have been achieved in solid wood alone. The veneer technique is completely dependent on adhesive. Without reliable glue, a veneer peels, splits, and is worse than useless. With it, you can take a piece of ordinary wood and cover it with something extraordinary, creating a surface that looks and feels like it is made from something rare throughout its entire depth. The ancient Egyptians were using glue not just functionally but artistically, as a material that enabled a kind of beauty that didn't exist without it. The luxury goods of the ancient world, the furniture, the inlaid boxes, the composite bows laminated from multiple materials to combine the flex of one material with the rigidity of another, all of those depended on adhesives that held reliably under conditions of heat, humidity, and stress. The animal glue used in Egyptian furniture was made from collagen, the structural protein found in animal hides, hooves, and bones. When collagen is boiled in water, it breaks down into gelatin. Allowed to cool, that gelatin solidifies. Heated again, it liquefies and can be applied as an adhesive. When it cools and dries in the joint, it forms a bond of remarkable strength. This is essentially the same chemistry as the glue that was used in European furniture making, in Chippendale's workshop, in every cabinet maker's studio, until synthetic adhesives arrived in the 20th century. Thousands of years of glue making using the same fundamental material, refined and improved across generations, passed down through craft traditions. Here is a connection that I find surprising and that I think almost never gets made. The history of glue is the history of the written word. Not in the sense of ink or parchment, those are different stories. In the sense that the physical survival of written knowledge across centuries and millennia depended on adhesives. A book is not just paper and ink. A book is a binding, the covers that protect the pages, the spine that holds the whole structure together, the signatures, the folded bundles of pages that are sewn and glued into a coherent object, the leather or cloth covering over the boards that form the cover. All of this requires adhesive at multiple points. Before the codex, the book format we still use with flat pages bound at one edge, the dominant form of written record in the ancient world was the scroll. Papyrus or parchment sheets glued end to end to form a continuous roll. The joints in the papyrus scroll were made with a starch-based adhesive, typically paste from flour and water. If that adhesive failed, if the joint dried out and cracked, moisture caused it to delaminate. The scroll broke, the text was interrupted, fragments became separated. When the codex form developed in the first few centuries CE, it required more complex adhesive techniques. Pages needed to be bound at their edges. Boards needed to be attached. Leather needed to be adhered to boards. The craft of bookbinding became, over centuries, one of the most technically sophisticated adhesive arts in the world. The great libraries of the ancient and medieval world, Alexandria, Constantinople, the monasteries of Ireland and England where classical manuscripts were copied and preserved, their entire function as repositories of human knowledge depended on the physical integrity of the objects they contained, and the physical integrity of those objects depended, at multiple critical points, on the quality of the adhesives holding them together. There is a direct line from a Neanderthal's birch tar to the survival of Aristotle. I don't mean that poetically. I mean that the physical objects through which Greek philosophy reached the Renaissance, the manuscripts copied and recopied, bound and rebound across 1,000 years of transmission, are objects in which adhesive failure meant knowledge loss. The monks who copied text understood this. The care they took with their bindings was not just craftsmanship, it was preservation. Glue kept the words of the ancient world alive long enough for the modern world to inherit them. By the 19th century, glue was an industrial product, and the industry that produced it had a problem. Animal glue, the dominant adhesive of the era, used in furniture, bookbinding, textiles, footwear, and dozens of other industries, was made from collagen extracted from animal hides, hooves, and bones. The raw materials came from slaughterhouses and tanneries. The production process involved boiling those materials in large vats for extended periods. And the smell was, by contemporary accounts, extraordinary. Not extraordinary in a good way, extraordinary in the sense that it could be detected from a significant distance, that it permeated the clothing and hair of anyone who worked in a glue factory, that entire neighborhoods downwind of a glue works had a persistent and unmistakable quality to the air. Glue workers, like tanners, like bone meal processors, like the people who worked in the industry that turned animal waste into useful products, occupied a peculiar social position. They were completely indispensable. The furniture factories, the boot makers, the paper makers, the piano manufacturers, none of them could function without the product these workers made. And yet the workers were socially marginalized, their factories pushed to the edges of the towns, their occupation regarded with a mixture of necessity and distaste. This is a pattern that appears throughout industrial history. The people who do the necessary but unpleasant work of turning raw materials into useful products are simultaneously essential and overlooked. The glue makers enabled the Victorian era's extraordinary output of manufactured goods. The smell of their work was the smell of prosperity, just not in a way that prosperity wanted to acknowledge. The industrial demand for glue in the 19th century was enormous. The furniture industry was producing at scales that handcraft had never approached. The shoemaking industry was mechanizing, with Hyman Mackay's shoe-lasting machine transforming production volumes but still requiring adhesives at multiple stages. The textile industry used size, a starch-based adhesive, to strengthen threads for weaving. The wallpaper industry, the packaging industry, the growing manufacture of musical instruments, where animal glue remains to this day the preferred adhesive for violin and guitar construction because it is reversible. A joint made with animal glue can be opened with moisture and heat, allowing instruments to be repaired. All of this ran on glue, and all of the glue ran on animal collagen, and all of the animal collagen smelled. The 20th century changed everything, as it tends to. The first synthetic adhesives began appearing in the early 1900s. Bakelite, the first fully synthetic plastic, was developed by Leo Baekeland in 1907 and had adhesive properties alongside its molding uses. Urea formaldehyde resins appeared in the 1920s and found immediate application in plywood manufacturing, allowing thin sheets of wood to be laminated together into panels of great strength and stability. PVA, polyvinyl acetate, was developed in Germany in the 1920s and became, by the mid-20th century, the white glue found in every school and every craft room in the world. The one in the white bottle that children have been eating in small quantities for generations to no apparent harm. But the adhesive that genuinely changed what was possible, the one that introduced a completely new relationship between materials, was epoxy resin. Epoxy, developed in the late 1930s and commercialized after the Second World War, was a two-part adhesive, a resin and a hardener that, when mixed, triggered a chemical reaction, producing a bond of extraordinary strength that was also resistant to chemicals, moisture, and temperature extremes. Epoxy didn't just stick things together, it created a new material at the joint, harder and often stronger than the materials it was bonding. And then in 1958, an American engineer named Harry Coover, who had actually first synthesized the compound by accident in 1942, while trying to develop clear plastic gun sights for wartime use, brought cyanoacrylate to market under the name Eastman 910. The rest of the world knows it as superglue. Cyanoacrylate is chemically extraordinary. It is a monomer, a single molecule that polymerizes almost instantly in the presence of the very slight alkalinity of moisture. When you apply superglue to a surface, the moisture on the surface triggers polymerization, and within seconds you have a polymer chain that bonds to both surfaces simultaneously. The bond forms at a molecular level, not just sitting on top of the surfaces, but interacting with them chemically. This is why superglue bonds skin so effectively and stubbornly. Skin is slightly moist and slightly alkaline. It is essentially the ideal surface for triggering cyanoacrylate polymerization, which is a fact that most people learn at the worst possible moment. In forensic science, cyanoacrylate is used to develop latent fingerprints. The fumed superglue reacts with the residues left by fingertips, making them visible. In emergency surgery, surgical versions of superglue adhesives are used to close wounds without stitches, particularly in situations where speed matters more than aesthetics. In the Vietnam War, medics used a cyanoacrylate formulation to seal wounds in the field. Superglue in a medical-grade form has genuinely saved lives in battlefields. This is the part that I think surprises people most, and it's worth understanding clearly. A bolt, a metal fastener screwed through two materials, holds those materials together by clamping force. The bolt passes through a hole, a nut tightens against the surface, and the two materials are held by the compression between them. This seems extremely robust, and it is under many conditions. But a bolt has a fundamental structural weakness. It concentrates force. All the stress in a bolted joint passes through the bolt itself and through the material immediately around the hole. Under vibration, under cycling loads, the kind of loads that occur in aircraft, in vehicles, in structures that flex and move, those concentrated stress points are where failure begins. The material around the hole fatigues, the bolt loosens, cracks initiate at the stress concentration point. An adhesive bond distributes force completely differently. Instead of concentrating stress at a single point, it spreads it across the entire bonded surface. The stress per unit area is dramatically lower. Under the same overall load, an adhesively bonded joint experiences much lower peak stress at any single point than a bolted joint carrying the same load. This is why modern aircraft use adhesive bonding extensively alongside and in some cases instead of mechanical fasteners. The Airbus A380, when it entered service in 2007, used adhesive bonding at multiple critical structural points. The Boeing 787 Dreamliner uses extensive adhesive bonding in its composite structure. Military aircraft, Formula One cars, high-performance bicycles, spacecraft all use adhesive as primary structural elements because the weight saving from replacing metal fasteners with thin adhesive films, combined with the performance advantage of its distributed stress, is significant. The entire outer skin of a smartphone, the glass front, the glass or metal back, the waterproof seals around every component, is assembled using pressure-sensitive adhesive and UV-cured optical adhesive. The screen of your phone is glued to the frame with optical clarity adhesive that transmits light without distortion. The battery is adhered to the chassis, the fingerprint sensor, the cameras, the speakers, all held in precise position by adhesives chosen for their specific combination of bond strength, flexibility, thermal conductivity, and electrical properties. Your phone is a composite object held together by a suite of different adhesives, each chosen for specific function in a specific location. It is in its fundamental engineering logic not that different from a Neanderthals hafted tool. Different materials joined together to achieve something neither material could achieve alone. Now let me take you somewhere even more interesting. Because everything humans have ever made with glue, from birch tar to aerospace epoxy, is by the standards of what nature has developed still quite limited. Consider the barnacle. A barnacle is a small crustacean that in its larval stage settles on a hard surface and permanently glues itself down. It does this in salt water, on surfaces that are constantly immersed, constantly exposed to turbulent mechanical forces, constantly subjected to the attempts of various organisms and eventually entire shipping industries to remove them. A barnacle once settled does not come off. The adhesive it secretes, barnacle cement, forms a bond that shipping companies spend billions of dollars annually trying to scrape from the hulls of their vessels, and that researchers have been trying to understand and replicate for decades. Barnacle cement is a protein-based adhesive that cures underwater, bonds to virtually any surface regardless of chemistry, and maintains its bond under conditions that would destroy any synthetic adhesive currently available. The mechanism by which it does this is still not fully understood. The proteins involved have been identified and their sequences mapped, but the precise chemistry of how they interact with surfaces underwater to form such durable bonds remains an active area of research. Mussels have a different but equally remarkable solution. They anchor to rocks in the intertidal zone, surfaces that are wet, covered in salt, frequently subjected to wave forces, and periodically exposed to drying. They do this with a bundle of protein threads called the byssus, each thread anchored by a protein adhesive plaque that bonds to the rock surface. The adhesive proteins, called muscle adhesive proteins, or MAPs, contain an unusual amino acid modification that is responsible for their underwater bonding ability. This modification, called DOPA, has inspired research into surgical adhesive and underwater repair compounds that could work in wet environments where conventional adhesives fail. And then there is the velvet worm. A velvet worm, an ancient lineage of organisms that look like caterpillars with stubby legs and have been essentially unchanged for 500 million years, hunts by firing rapid hardening sticky slime from modified limbs on either side of its head. The slime jets out as a liquid, wraps around the prey, and hardens almost instantly into a fibrous mesh that immobilizes it. The mechanism is remarkable. The slime is a protein solution that transitions from liquid to solid through a physical process triggered by the mechanical stress of being ejected at high velocity. Not a chemical reaction, a physical one. And honeybees have found use for adhesives that is, depending on your perspective, either deeply practical or genuinely disturbing. Bees collect plant resins and process them into a material called propolis, a sticky antimicrobial substance used to seal gaps in the hive, coat the interior walls, and plug entrances against pathogens and small intruders. Propolis has potent antibacterial and antifungal properties and keeps the hive environment remarkably clean. But its most macabre application is this. If a small animal, a mouse, a large insect, wanders into the hive and dies and the body is too large for the worker bees to remove, they will completely encase the corpse in propolis, coat it entirely, seal it off from the rest of the hive, mummify it essentially to prevent decomposition from affecting the colony's health. A bee uses glue as a mortuary tool. Nature has been exploring the adhesive design space for hundreds of millions of years, and the results make our best synthetic adhesives look like early experiments. Let me end where we should end, with the thing itself. Glue never conquered an empire. It never sparked a revolution. It never got its own chapter in a history textbook or its own exhibit in a museum. It held things together quietly, invisibly for 200,000 years and has never once demanded credit. But think about what would not exist without it. The composite tools that gave early humans a decisive advantage in hunting, gone. The Egyptian furniture that has survived 3 millennia, gone. The manuscripts that carried classical knowledge through the Dark Ages, gone. The violins of Stradivarius, assembled with animal glue chosen for its reversibility, gone. The aircraft you've flown in, the phone you carry, the book on your shelf, the shoes on your feet, all of it held together by the quiet technology, by the material that joins different things into something neither could be alone. There is something almost philosophical about this, the great transformations in human history, the ones that genuinely changed what was possible, were often not the dramatic, visible inventions. They were the enabling technologies, the things that made other things possible. The wheel gets the credit, but the grease that let it turn smoothly is just as important. The printing press gets the credit, but the glue that bound the books it produced preserved what it printed. The computer gets the credit, but the adhesives that hold its components in precise alignment make it function. Glue is the enabling technology underneath every other enabling technology. The material that says these two things which cannot be one thing can work together as if they were. A Neanderthal 200,000 years ago figured this out with birch bark and a fire, and nothing has quite been the same since. So the next time you pick up a glue stick or peel the backing off a self-adhesive surface or notice the line where two materials meet and hold, just take a second. You're using the oldest synthetic material in the history of life on this planet. A technology older than our species, one that held the words of Aristotle together through 1,000 years of copying and binding, one that joins the glass to the frame of your phone, the sole to your shoe, the veneer to the surface of the table you work at. It never asks for recognition, it just holds. History isn't only in museums, sometimes it's in the invisible line where one thing meets another and stays. If this made you think about something you've never thought about before, that's always the point. The Hidden Life of Things is on Spotify, Apple Podcasts, and wherever you listen. A follow or a like genuinely helps, and if someone in your life is the kind of person who looks at ordinary things and wonders how they work, this is their podcast. And here's your clue for next time. It has fed more humans than any other food in history. Half the world eats it every single day, and yet it is almost invisible in Western culture, treated as a side dish, a background carbohydrate, something unremarkable. In the places where it actually matters, it is anything but. It has been used as currency, as a tax, as a symbol of power so potent that who controlled it controlled entire populations. The way it is cooked varies so dramatically between cultures that the same grain becomes almost unrecognizable across different kitchens. And the genetic modification of one variety of it, carried out in the later half of the 20th century by a man most people have never heard of is estimated to have prevented 1 billion deaths. What is it? Stay curious. I'm Alexandra, and I'll talk to you next week.